surface up here, put a tree there, and this is where streams deliver detrital sediments, detritus from the land surface along with the water. And here's the shoreline. So this is the ocean basin out here to the right. You probably know that there is a shallow, 200-meter deep platform off most continental edges called the continental shelf. And so the river-delivered sediment is further redistributed out on the continental shelf, many tens of kilometers by ocean currents and things like that. It will grow up or accumulate through time, and if there's a seismic event, if it's a tectonically active coastline like the west coast here in California, Oregon, and Washington, or in the east coast, maybe the sediment builds up until some internal threshold of strength is exceeded and it fails. It will avalanche, it will submarine avalanche down what's called the continental slope, and it will have enough inertia that it will carry it forward out onto the abyssal plain. And so that submarine avalanche that starts here, moves down the slope and out onto the abyssal plain is known as a turbidity current, a turbid current, a suspended sediment current. And so what I'm going to do is generate exactly that, starting in my model up here, sort of the edge of the shelf. So this is the continental slope, and then this would be the abyssal plain. Okay? Now, that turbidity current, as it moves down the slope, if we could enlarge this part of the diagram, and here's the slope, this moving cloud of suspended sediment is known as a turbidity current. And they've been calculated to move 60 kilometers an hour, which is 36 miles an hour, 40 miles an hour. You may not appreciate this, but your grandparents certainly do. If they ever tried to make a phone call from North America to a friend or relative or a business partner in Europe, this in the 1940s, 50s, before satellites, it was by cable, copper cable, transatlantic cables. And so cable companies know the position of their cables across the ocean floor. And when one of these things cut loose, the first few, of course, they had no idea what was going on. All of a sudden, conversations would break. And if you know the location of the cable and the precise time of the break in a series of cables, knowing the distance, knowing the time, can't we convert that to a estimated velocity? And in fact, that's how it was done. There was nobody down there in a submersible clocking these things and filming them because you're under thousands of meters of water in a totally dark environment. And these are fairly big events. So just by sort of a quirk of history, these breaks in these transatlantic cables gave us these numbers. Now, these turbidity currents, of course, will eventually come to an end. And so typically, as you move from the high energy slope down to the lower energy abyssal plain, you're going to start to get rapid deposition down here in a series of very thin beds. These beds are known as turbidites. So the mechanism, the transporting current, the mechanisms of turbidity current, the product, the geological thing that's produced is a turbidite. And turbidites are recognized because they are basically stacked graded beds. This is analogous now to the experiment that I have running on the front whiteboard in the classroom. And a graded bed, you will see if you haven't looked at that settling tube, has sand on the bottom, silt in the middle, and clay on the top. It gets finer in an upward direction. And the scale here is only typically centimeters. So what you're seeing demonstrated in that big settling cylinder in class is a mega graded bed, if you will. Now, of course, on my model, you can see that there is a thin sediment layer that's been deposited on the plexiglass from my prior two demonstrations. You may further notice that a lot of the coarse grain debris stopped right there. And that's an area of this model called the rise. So if you're out here on the abyssal plain, it gets slightly steep as you walk up the rise, and then it gets steeper as you head up the slope. So that rise is basically similar to a submarine alluvial fan. Remember alluvial fans today that you saw at the base of the mountain on the land? Well, we have a similar landform on the bottom of the ocean. So what I'm going to propose is that if you want to take a picture of this thing, I'm going to get my secret sauce, which is really nothing more than a mud slurry, and I'm going to introduce it rapidly here, which is meant to simulate the edge of, or point of failure. This, of course, is the slope, and that's the abyssal plane. Yeah.
Is that word tack, T-A-K?
Tail.
Oh, the tail. I'm sorry.
Tail.
The head and the tail.
Oh, that makes sense then. I
Yeah.
was like,
So this thing, you're going to see this thing move as an integrated body, and it's going to remain separate from the water column. It's going to be remarkable how this dense turbidity current doesn't really mix with the clear water column through which it's moving. And so you can see a distinct head and a distinct tail to these features. Mind you, this is really exciting, so hang on to your hats. You ready? Ready. I'm going to do just a real quick introduction, and
I'll do the ooh, you do the ah.
there it goes. So you can see how distinct the head is, and you've got this attenuated tail. And look how it remains pretty much coherent as it rolls across the landscape there.
That is pretty cool.
it's kind of like a vortex.
Yeah, it's a counter circulating head on that thing, and so it actually scours. It has enough energy that it actually erodes a little bit in front of it and incorporates some of that sediment into the body of the current. Now, of course, my flume has a wall at the end that the ocean does not, and so this thing will bounce back, and you can see the results of the first two experiments sort of silting up the water column.